Okay, so I'm just going to try and get this started, get it sorted, and just think out loud for a bit, okay? So this is where I started this morning. Basically, we need a Kagome material, which if you don't know what that is, Kagome materials are things that are metamaterials. That means they can change from one state to another, usually through a combination of covalent bonds and all that jazz. Basically, if it's like the self-healing screens you see on cell phones right now, you know? It's not nothing too crazy, but you can do some really cool stuff. You can make stuff transform into other things and transform back based on heat, based on position, based on time structure with combinations of either. You also need the meta lens, and you need a parallax between points in space-time for this system to work. What are we calling this? I don't know what to call this yet, so whatever. This is anyway. So we have a meta lens here. This is meta lens 1. Oh wait, I'm not even on the page. 1 second. Meta lens 1 here, and then we have like something like the James Webb Telescope looking through on the endpoint to meta lens 2. So we'll say that's meta lens 1. We'll say that's meta lens 2. We'll say that's parallax. All right. Sorry, you're gonna hear my chair squeak if you do. It's just a very sensitive mic until I get the level sorted out. But whatever. Actually, is this turned on? Yeah, it is. Okay, cool. Right. So you'll need that. You'll need parallax between them. So basically, what you have in the interim is you have this point here, this inflection point here, and that's going to be your gravitational lens. Oh, I already put it down here, so we don't need that part up here. Like that's your gravitational lens. Is this little point here, this point of inflection? Yeah. And at the same time it's doing that, you have to realize that because gravitational lensing is it is an asymptotic formulation of gravity from a certain perspective, i.e., our perspective. So say we have that. It means that from one perspective, say ours on Earth 2, let's say Earth 1 over here, Earth 1, right? We're going to go down here, and it's going to go, because we're looking at it from our perspective towards it, it's going to go down in one dimension. And from them going in the same dimension, it's going to be going from an opposing point on planet 2, we'll just call it Bob, because why not? Oh, or I could spell that better, but basically what you're going to have to do is do this for all the dimensions, because there's not just one. Oh, sorry about that. There's not just one. There's a few. That's one dimension, right? So you have that point here and this point there. And what can I draw this yet? Okay. So you have that. And then you have gravitational lensing. And the thing about gravitational lensing is that on one side it's completely dark, and the other side is completely light, because what you're seeing is the smear and the you know the horizon. Sorry, you're seeing the lensing around a black hole, and I've only noticed this because of my own work in computer vision with stuff I sent to NASA, who have been sharing it with friends and stuff, and they've been sharing it with colleagues at NASA. I tried to send it to the ESA, but I don't have any contacts there yet. So, but yeah, so we have 4 dimensions, and I'm just kind of working my way through this stuff as I go. So just bear with me. But the end goal is to have you're gonna have all dimensions mapped, right? So you're gonna have time x, y, z, and this is going to be negative z, negative y, negative x, and this is going to be negative time. If I can spell that correctly, let's make that clear. Negative time, right? Because here is your inflection point. That's your inflection point that you really care about. That's your meta lens, remember? So we have Earth, and then we have our meta lens, and then we have our little inflection points of all points going here, and then we have a time that is going forward, because it takes time for us to measure, right? Because that's time. And this is x, y, z. That doesn't look like a y again. Sorry about that. And we have, so then we have to know, so then for them, if they were viewing us at the same way so that we could both see each other at the same time, they have to have this. That's to see each other at the same time. Okay. All right. So we have that, right? So if we want to see each other at the same time, we got to figure out the inflection point of where the whole is 1 at the time is 0, negative time is 0, negative z and z are 0, x and negative x, straight negative x are 0, and negative y and y are 0, right? Sorry for the confusing patterns there. But as we go, we're going to find that their time differentials are different, their gravitational differentials are different, they're just pretty much anything from the... Oh, did it again. Sorry about that, I'm struggling here a little bit. We have to use an imaginary... You have to use an imaginary E equals mc squared because you need a gravitational... You need a gravitational constant equals mc squared, yeah. Because on theirs it might be something crazy because gravity is different relative to the heat index ratio of the universe and the expansion of the universe and their local version of gravity. Because as we get closer to the center of, or sorry, to the beginning of the Big Bang, it's a lot hotter, there's a lot more action, the gravity might be a lot stronger, it might be a lot less, because, you know, plasmas and all that stuff. So what you have here is you have mc, instead of squared, I did a to the power of b, because some combination, I might draw that a bit better. It looks like c a to the b. All right, we'll do that. That might not look clear to you. Sorry, I'm just going as I can. But yeah, we can effectively just rewrite stuff a little bit better. And I'm okay. So what was I doing? We were doing dimensionalities with the Justin Webb telescope or the Hubble telescope or any of them. Cool thing is we can take 2 points, so we can take like Justin Webb telescope and the Hubble, because if they're both in action still, right? And we can, those are our anchors for space-time, right? This one sees a lot farther. This one sees not as far, but there's a point where they mesh, and then that's our inflection point. And there we get time 1 and time 1, and we sync those with atomic clocks, right? And that's just an atomic clock. Come on. Sorry, my table's shaking. Atomic clocks, quantum entangled. Right. So we have that. So we have an inflection point. We'll have this be our, I don't know, we'll have a z, x, y, because what we could do is we could have this, and then that. Okay, yeah, I think that's what we'll do. We'll have this be our x1, and then we'll have this be the James Webb telescope, and we'll have this be the x2 of the Hubble, just for an example, because I'm not sure what's active right now. And then here, for each of them, we'll have the y2 be the redshift, right? And the this is going to be a little bit messy. Come on. We'll have the z2 be the blue shift, or we'll do something else. It'll be some other shift. It'll be something else. And then for here, we'll have z1 be, because they have to cancel each other out. So you can't have blue shift cancel out blue shift. You have to just flip them. So that has to be, yeah, I think that has to work, because that would find your distance. That would cancel out the red shift and the blue shift. Yeah. So that would be red shift. Sorry, a little backwards here. Red shift, and then what's that one? That's y1. Blue shift. Anyway, it's not too complicated. It's just a bunch of parallax. So what we have here is we have red shift and blue shift cancel out, and converge at x value x1. Now this part I don't quite know how to do. x1, x2. I think it's just the 2 over x of atomic 1 and atomic 2 over the average of the atomics. So that's a bit messy because I'm coming up on the fly, but that's the inflection point for now. Right? Nothing too crazy. This is of course going to need review, and better people are going to make better stuff than me. But anyway, so what we have here is we have that, and right, and then those actually have to be here and here, and these have to be connected. Yeah. So that's how you find one point, and then I should erase this. I think. I should erase that. Maybe. I don't think we need this right here right now because we're just trying to figure out what we're doing. Okay, so we got that part down. Here, and append that. Okay. So we have this, and it's like, okay, so we have some kind of like the beginnings of stuff, and we can now see into a point into the future, X light years away. All right. Here, ta-da. With no shift, with no, it's lossless because the goal is non-relativistic loss because we're just trying to sync up the lenses and get rid of the shading errors, which we can do I think pretty naturally now with all the GPUs we've got and the hardware we have. So anyway, so we have that. So we have, let me just try and draw it bigger so I can see what I'm doing. So we have x1, come on bud, x2, z2, y2, and this is z1, and this is y1. Okay. Okay, so then we have all that. On the other end, all we're looking for, because we have to do the same thing. So we have, this is t of 1. This is also t of 1, but it's also t of negative 1, right? Because to us, it's in the past, but for them, it's in the future. Because as we go forward, it's going to go to t2, which means this is going to go forward to t2. And because this is going in the same direction, but it's negative, it's going more negative, right? It's going to the t of negative 2. So that's only as we're progressing this way. So what we have here is the same thing, but then we just reverse it. So for this, we need to know what we're looking for. So let's say we're scanning for life on other planets in reverse, because we need to know if they've killed themselves or if they've had bad luck with the dinosaurs in reverse. And that's the Fermi's paradox, right? It's like what is there and how do we get there? Okay, so we have that, right? So right. So we need to go more negative. We need to find so we have this planet here. This is us. We have all this information. We've done all this jazz. Come on. So here and here, that's James Webb Telescope, and this is Hubble, or anybody really, doesn't quite matter. And then we have our inflection point. So then for the same thing, we have here and here. Just remember that these are flipped. So now this becomes x2, okay, these are all negatives. It's the same thing, negative x of 1. Oh wait, that's 2a. Yeah, it's negative x of 2. See what I mean? And this is negative x of 1. You know, I might just, no, because you need to know that they're different. You need to know that seeing one thing is the same thing as seeing the other thing, because that's what you're viewing through. Because you actually have to warp around the black holes, and you have to warp around the gravitational lensing. Because if you don't, you're just gonna stare at them and be like, well, I'm in the event horizon and I can't get out. It's like, yeah, because you went too far in, and you're not looking at it as a smear of light. You have to unsmear the light. So it's a little, it gets okay. All right, we'll get to that part too. But yeah, so that's that, and so that means that this is negative. Let's make that clearer. This is negative z2, negative. Let's try and make this clear. Negative 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 y2. What is this? Oops, sorry about that. Negative y. My brain is not firing. There we go. That's that one, and then this one is negative z1, and this one here is negative y1. Okay. So that gives us their inflection points needed to then go from here to here, and we'll say this is the planet's, I don't know, we'll say this is radius 1 and radius 2, and that gives us this viewing angle here of what is it? Its circumference is 2dr. Is it 2dr? No, diameter is 2. I can't remember. Anyway, it's half the circumference of the. It gives us our viewing panel. It's basic stuff. I'm blanking right now because I haven't practiced in a while. But anyway, so then that means that we have planet X, and then we can see into it. And then if we want to go further back in time, we just lock those positions, right? So then, okay, new page. To see back in time over space-time, we adjust red and blue shift with machine learners. So, yep, and that means with, by the way, not and. With tracking and yeah. Now that gives us a straight view, right? That gives us a straight view from any point to any point. Okay, so so we don't need that part with learners and tracking. Yeah, okay. And you ask, how do we? You say, well, how do we see around black holes? Okay, so you have that, you have this, you have this, you have your burn off, and you have your other burn off. This is the front, right? Okay, that's the light. This is all the light we're seeing up here. And this is all the light we're seeing up here. Now, if you go to the side view, what you're seeing, if then this is going to be a little bit, this might be a little bit esoteric because I'm just, or enter. So it's same view, side view. That's this part, right? This is this part down here. It's actually pulling it all in. And I may not be able to draw this all in. All right, and we'll do this one here. And this is pulling it all in. Right? Because it's actually hitting a gravitational constant that is so strong that nothing escapes it, right? To our current knowledge. So this is a side view. Maybe do I have space for this to say side view? Side view. This is front view. That's side view. Oops, my bad. Ugh, looks terrible. All right, come on, hand. 1, 2. All right. So side view, right? So that's the light coming in, like, which means the back. So this is now the back. Is just well, okay. It's gonna look completely dark. right? And that's what we see when we see. I can show you in the videos that I've made with my computer vision system sent to NASA. I can totally show you all of this. You just have to ask me and I'll figure it out. And we'll make the video. Yeah, anyway. So what you actually don't notice yet is that because this is complete darkness, this is the back, right? No light. So, because there's nothing, because no light makes it, outside light reflects from it. Reflected, or I should say reflected from it. So I'll show you an instance. It's actually on my YouTube channel somewhere. You'll see them when I circle things like this, and then it's like this. That's a reflective one, and you start seeing them in space-time videos pretty much all the time once you realize what they are. Once you can do the parallax between black holes, you'll start to see the patterns of constellations in the past and how they've rotated. And then you'll see how the curvatures are, because you'll see the little smeary things, and then those smeary things will lead to these little circles. And it's like, well, what are the circles? And they're reflective. Some are empty and completely dark, and that's like, oh, that's the backside of a black hole with nothing in it, because black holes, they just like a coin being flipped, right? Yeah, it's reflective, and it's reflective, and it's reflective, and it's reflective. But here, let me draw this a little bit better. Yeah, I mean, well, that one's just ugly. Whatever. Black hole. Oh, whatever. I'm gonna start this part over. Anyway, so we have these black holes. Where was I? No light. Okay, because no light makes it outside light reflects from upon it. I should say actually. Oops, that's the wrong page. Upon it, upon surface. All right, there we go. So what you'll notice in the videos that I'm making, with I believe I called it Sentinel. No, Sentinel was actually to figure out how many planets there actually are in the universe, and how many stars I've mapped out already. And then I used that information and my knowledge in computer vision, which I'm quite good at, to design a methodology and basically just an algorithm and a vision system that uses the data that I can get from NASA and USA and all that publicly, through Gaia and the other systems, to show that if you fold back the universe, there's not that many patterns. It's just a thing to know. Anyway, so what were we talking about? See, this is the thing, I get distracted just like anyone else. So we were talking about how to see around black holes. Oh, okay. So we have the front. We know that. We know this is light. Am I in the wrong layer again? Sorry, I am in a bit of a quagmire. Light. Front. Light. Just say light and matter, huh? We'll say light, and we'll say light and matter. Not bad. Light and matter. Okay, yeah. So we have that. So if you want to see around them, you actually have to. So the thing is, they're moving in space. Okay, so black holes still move through space-time relative, and this is simple to everybody, right? Because everyone knows this, or relative to their past selves. I mean, an object in motion stays in motion, right? To their past motions. Right, so object in motion, in motion. Object in motion stays in motion until stopped. Okay, so we have that. So the thing is, so they rotate and transform based on increasing, I should say fluctuating, not just increasing, because you don't actually know yet, fluctuating gravitational systems. Okay, got that backwards. Come on. Gravitational systems, and systems and energy absorbed. Sorry, I always spelled that wrong. Absorbed and expelled as Hawking radiation. So they move. So they, like a coin. Like a coin being flipped. Forgive me for the cruddy info-ness, but whatever. So we'll have light side, dark side, light side, dark side, light side, light, dark, light, dark, light. Now that's so remember, so light is what we know now, and dark is the reflection from nothingness, from no light, from nothingness. I'll have to say it like that because if I say light in the definition, it gets confusing. Nothingness. Okay, I think I'm going to stop here just to make sure I have enough hard drive space to upload this. Yeah, so I'll put this up on my YouTube channel. This is going to go on to Townsend's Designs LLC. Please come find me on YouTube. I'm happy to answer questions, happy to figure this out with you, happy to do peer review. If you want to sit here and degrade it, please don't waste my time. I don't have the energy to fight you on semantics. This is not a challenge. This is not like an FU. This is like, hey, look, if you don't understand it, that's cool. If you think it's wrong, that's cool, but I don't have time to sit here and explain to everybody why you think it's wrong. But if you think it's wrong and you have this, and this, and it's like, well, this is because of this, and it's like, oh, I didn't know that. That's awesome because I'm learning as I go, just like anyone else. But just like the internet wasn't for fighting; it was so we could meld minds, right? And this isn't Reddit. This is me trying to make science with you, with everybody. So much pleasure. Come check me out at linkedin.com/in/discussions if you want to chat. Yeah, and just remember, I'm a person just like you are, and I make mistakes, and I have off days just like you do. So much pleasure, and I wish you all the best. Bye.